right, welcome back to the night class. Today we're learning linear and angular velocity. What's velocity? What's the speed? Okay, so linear speed is how fast you're going in a straight line. And what is angular speed?
How fast you're going at an angle.
That's how fast the angle is changing, actually. Okay, so two different types of speed, and we're going to kind of learn about them. It says here, the Children's Museum in Indianapolis, Indiana houses an antique carousel. The carousel contains 3 concentric circles of animals. Concentric, ooh, geometry word. Remember, circles that share the same what? Center. All of these are concentric circles. You know it as a bullseye, okay? That's the concentric circles, okay? The inner circle of animals is approximately 11 feet from the center, and the outer circle of animals is approximately 20 feet from the center. The carousel makes 2 5/8 rotations per minute. Determine the angular and linear velocities of someone riding an animal in the inner circle and of someone riding an animal in the same row in the outer circle. So, carousel, right? Everybody rode that at the fair, okay? You get the horses, or you know, like my kid, they fight over the dragon, okay? So whatever you want to ride.
To the fair yet?
I have not this year. So which you may know this, you may not. Let's hypothesize whose velocity, angular and linear velocities. Well, whose linear velocity do you think might be greater? The guy riding on the inside or the guy riding on the outside? Outside? Okay.
Well, what's the question?
Whose linear velocity is going to be faster? The guy on the inside riding the horse or the guy on the outside riding the horse?
Outside.
Faster?
Okay. Faster.
The inside.
Inside? All right. Let's look at something that's not exactly the same, but let's check out some ice capades here real quick. Okay? So this is basically what's happening. Okay? There we go. So notice how much work are the people on the inside doing? They're just kind of taking a stroll, and the people on the outside were really skating.
How did you find the ice cadets?
It's really this thing called YouTube. You just type in ice capades,
No.
but notice how hard they're skating on the out. Well, let's go back up just a little bit. See the people in the very center? They're just walking, but the people on the outside, they're skating. Okay, and they're skating pretty hard because they have to. Why do they have to skate harder? Well, it is because they're on the outside, but there you go. That's the answer. Okay, did y'all hear what he said? They are traveling a further distance. Okay, but Caden Fant said that. Yes, thank you, Caden Fant. All right, so this guy on the inside, he's just traveling this circle, while the people on the outside are traveling the big circle. Okay, but they have to stay in line, right? So in order to stay in line, this person has to go faster because he's got a greater distance to cover than the guy on the inside. Is that making sense? Yeah. Okay. All right. I usually have, sorry for you viewers at home, I can't do this for you, but, heads up. Oh, this is what I love. Okay, so if you have a slingshot, right? Okay, it's just a ball. Okay, it's a ball. All right, I'm putting it in this towel right here.
Whoa.
All right, and yeah, see it? It's right there. I did have a rubber band up here.
I know because those things say wording is beautiful.
All right. So right here, okay. This has angular velocity. Hadley's backing us. This has angular velocity, okay. but at the same time it has linear velocity. Okay? What happens if I let it go?
It's gonna fly.
What direction does it fly?
Well, what time to let it go? Because if it that way, it's gonna shoot. Because like
In a what?
Straight line.
In a line. Okay? Okay, so as soon as I let it go, it goes flying in a straight line. Okay? So understand, the whole time you have angular velocity and linear velocity going on at the same time. These angles are turning at some speed, but it's actually moving in a straight line at any point while it's going around a circle. Is that making sense? Okay? If I just let go of it, it's going to go knock, the squirrel or whatever you're trying to shoot with Goliath, whoever. Okay, it's going to go in a straight line and hit. Okay? So, that's the difference between the linear and angular velocities. Now let's find them. Okay? So, very, very simple. You have the first thing we're going to do is something we did the other day, is figure out how many degrees it goes in one rotation. But remember, this chapter we're not doing degrees, we're doing what? Radians, okay? Radians, I like that. All right, so it says determine the angular displacement in radians of 4.5 revolutions. Well, 4.5 revolutions is just another word for rotation, okay? And the angular displacement means through how many degrees, or in this case, how many radians does it go through in 4.5 revolutions, not revelations. So we got 4.5, and what do you think we might multiply that by? 360. That's what though? Degrees, okay? We want it in radians. So how many degrees, or how many radians is 360 degrees? 2, not 2 pi r, just 2 pi. Okay? So all you do is multiply it by 2 pi. It says round to the nearest tenth. You put that in your calculator. Boom, boom, boom. You get 9.17. Okay? So about 9.2.
How do you get that?
You put 4.5 times 2 pi. Maybe I looked at the wrong thing. My bad. I'm sorry. That is wrong. It's 28.3. You're right. That didn't even make sense, did it? Because 4.5 is... Yeah, that didn't make any sense. 28 point... What was it? 3? 28.3. Okay? And that is radians. So, in 4.5 revolutions, we're going to go through 28.3 radians. Again, it's exactly like you were doing with degrees earlier in chapter 5, but now we're in chapter 6, so everything's in radians. Everybody good? Okay? So, that's how far we travel. Okay? So, we're going to take that next and figure out angular velocity. This is your angular velocity formula. Okay? Has some cool little Greek letters. This right there, that's an omega. Okay? The little W looking thing. All right? Omega equals theta. What do you think theta is? That's your angles divided by time. Any velocity or speed is distance divided by time, right? Okay, when you're going down the road 60 miles an hour, that means every hour you're going how far? 60. That's how far you go divided by how long it takes you. Does that make sense? Okay, so we're doing the same thing. We're just figuring out how many angles are we going through divided by how long it takes us to go through them. Everybody with me so far? Okay, so let's try one. We got example 2 right here. Again, I got my formula there. Determine the angular velocity if 7.3 revolutions are completed in 5 seconds. Round to the nearest tenth. So first we got to figure out how many radians we go through. Did they tell me how many radians I'll go through?
10.
No.
It says revolution.
It says 7.3 revolutions, but is that a radian? No. So what do we have to do with that? We have to multiply it by 2 pi. So 7.3 times 2 pi. Okay. Everybody understand why we're doing that? That's the example 1 right there. Okay, to figure out how many angles it goes through. Okay. It's going through 7.3 times 2 pi radians because we're doing 7.3 revolutions. So 1, 2, 3, 4, 5, 6, 7.3. Okay. How many radians do we go through doing that? Well, we multiply it by 2 pi. Divided by how many times? What's the time? 5 seconds. Okay? So, put all that in your calculator. This is the one you should get 9.2 when you round it to the nearest tenth. Now that's 9.2 what? What's on top? Radians. What's on bottom? Seconds. So radians per second. Okay? Most of the time we measure distance or speed in miles per hour because we live in America and that's what we do. Okay? If you go to Germany, it's kilometers per hour. Okay? They sell you gasoline in Germany by the liter. Okay? You don't pay per gallon, you pay per liter. Okay? It's just the way it is over there.
It's cheaper than
It's the same. Well, conversions is about the same price. Everybody good with what we're doing so far? All right.
I thought it's called petrol in there.
Petro, yeah, same thing. All right. Example 3 says, refer to the application at the beginning of the lesson. Determine the angular velocity for each rider in radians per second. Now, I'm going to scroll back up here, okay? Here's that example 1 again. Y'all listen. We already said the linear velocity, the guy on the outside is going faster than the guy on the inside, right? What about the angular velocity of them? They are the same, okay? It doesn't matter where you are. If you're on the inside or the outside, the angular velocity is going to be the same because they're going through the same amount of angles in the same amount of time, okay? But the linear velocity is different. Is everybody with me? Okay? So, example 3, they want us to find the angular velocity, which I guess I could do it right here. They're going through how many rotations? 2 5/8 rotations per what? Per minute. That's all I need to get my angular velocity. So, W equals my theta over the T. Theta is going to be, I done forgot it. What did it say, 2 5/8?
Yeah.
So 2, I can't draw. Try this again. Two 5/8 times what again? 2 pi over, what was our time? Per minute. 1 minute. Okay? And remember that cool little thing I showed you earlier on the calculator? You can put 2 5/8 in your calculator just like it is and multiply that by 2 pi. Last thing you should get is 0.275. And that is radians per, oops, that's wrong. I was supposed to change it. Because the question says, what is it per second? So, let me grab my calculator and figure out what this is per minute. Actually, you know what? I'll just keep going here. So, times all right. How many minutes or how many seconds are in a minute? 60. So I'm going to have 1 minute up top here divided by 60 seconds. And that will give me my seconds. Okay? Does everybody understand why we're doing that?
So basically, you can cross out the minute.
Correct.
Got it.
Minutes go away. Okay? I'm left with radians per what now? seconds, which is what we want. So
So you just do 2 and 5/8.
you do 2 and 5/8, yep,
Divided by 60.
divided by 60. 2 and 5/8 times 2 pi, divided by 60. And I got 0.275, okay? And again, that is going to be radians per second. So always be careful of what units you're using, okay? It could say radians per second, it could say radians per minute, it could say radians per hour, all right? Radians per day, anything like that. So just make sure you're answering the question that they're asking, don't be like me. Okay? Everybody good so far? All right, let's talk about linear velocity. Oh, I'm sorry. Yeah. They're still going? Sorry. Didn't get it plugging in? All right. Example 4, we are finding linear velocity. Linear velocity is S over T. Now, S, I don't know why they used S. It's distance, okay? Velocity is distance divided by time, okay? Or distance is velocity times time, however you want to think about it, okay? Your distance would be velocity times time, because if, let's say, you're going 60 miles an hour for 2 hours, how far did you go? 120 miles, okay? That's just basic stuff right there, all right? So, notice what they're doing here. We found yesterday the distance around a circle, okay? We used this little arc formula. Y'all remember that? S equals r theta, okay? That is why they're using S here. Because when you're talking about circles, that's how far, that's the distance you're traveling. You got me? Okay? So that's why they're not using D. They're using S in this formula. Because they're relating it back to yesterday. All right? So S equals r theta. That is your distance. Okay? So they do a little math here. Okay? They divide both of these by what? T. All right? And there's your velocity. You multiply r times theta over t, which is basically what we did yesterday, your arc length divided by the time. Okay? That is your velocity. That is your linear velocity. So this is how far we're going in a straight line. Okay? So I'm going to make this a little easier here. Okay? Make it a little bigger. Everybody good? Okay? We just had a formula that was theta over t. What is it? The angular velocity. Remember this thing? Theta over t. Y'all remember that? We just used it on example 3. Okay? So, another way of thinking about linear velocity is it's just your radius times your angular velocity. Okay? Because radius times theta over t, well, theta over t is your angular velocity, so it's just your radius times your angular velocity. Everybody good with that? Okay? So, you need to know both of these because they might give you information. They might just tell you the angular velocity, or they might tell you the angle and the time and the r. Okay? So, depending on what they give you, is which one you use. So, let's do example 4 right here. It says determine the linear velocity of a point rotating at an angular velocity of 17 pi radians per second at a distance of 5 centimeters from the center of the rotating object round to the nearest 10. Now notice, they gave me the angular velocity. So it's just plugging in. Okay? V equals R times the angular velocity, which is omega. What was my radius? What was the distance from the center? 5 centimeters. So 5 centimeters times my angular velocity of 17 pi. Okay? Radians per second. So my velocity, if you multiply those, let me see what you get. 267. What are we rounding nearest tenth? 267 point, it says it's 0.03, so about 267, and that would be centimeters per second. Okay? Centimeters per second. Why aren't we using radians in the answer? Radians measure what? Angles, and we're not measuring the angular speed, we're measuring the linear speed. Does that make sense? Okay? Everybody good? All right. Last one. Example 5. Refer to the application at the beginning again. Okay, so we're finally going to figure out the rider on the inner circle, we want their linear velocity. The rider on the outer circle, we want their linear velocity. We should know if we do it right, whose should be faster. The one on the outside should have a faster linear velocity. So, my radius for the inner circle, do y'all remember what it was?
11.
Are you sure?
I'm pretty sure.
All right. 11 times my angular velocity. We already found the angular velocity in example, what was it, 3? Yeah. Example 3. How fast were we going? 0.275. 0.275. And that was radians per second, of course. Okay. So this would be 11. Here? Yeah. No, because that's what I'm saying. We already found it up here. We already did the pi in example 3. Okay. Right here, we found the angular velocity for the carousel. So here was our pi. You got me? So we've already found it. We've already put the pi in. We're just using the answer we got from example 3 on example 5. Okay? So 11 times 0.275 would be about 3.025. Okay? And for my one on the outer circle, what was its radius? 20?
Yes.
So 20 times 0.275. Forgot my 5 there. Put that in your calculator. It is about 5.5. So is our outer velocity faster than our inner velocity?
Yes.
Yes, just like it should be. Okay? Everybody good? Awesome. If you'll look, we're going to do a few problems together. 6, 7, 8, 9, 10, 11. All right? 6 and 7 says determine the angular displacement. I'm just going to show you what that looks like. Hopefully over here somewhere. I've lost it. Where is?
Is this all out of the book?
Yeah, this is out of the book.
This is not homework.
This is not your homework.
Oh.
So, number 6, they told us we went 5.8 revolutions, so how do you figure out how many radians that is? You multiply it by 2 pi, okay? The revolutions cancel. 2 pi times 5.8, you get 36.4. All right? Same thing on number 8. Number 8, we go 710 revolutions. Same thing, multiply it by 2 pi. The revolutions cancel. 4,461.1 radians. Everybody cool on how to figure out how many radians? All right? 8 and 9, you're finding angular velocity. Okay? They give me everything I need. It says it goes 3.2 revolutions. I have to multiply that by 2 pi to get my radians. And it tells me it takes 7 seconds. So I divide it by 7, 2.9 radians per second. Okay? Literally all this chapter is, or all this section is taking what they give you, plugging it into the formula. Put that in your calculator, give me the answer. Okay? Don't make it hard. Same thing on 9, we go 700 revolutions. Multiply that by 2 pi to get the radians. Divide that. They said we went 15 minutes to do that. Okay? So 293.2 radians per minute. Very important you label this one's radians per minute, this one's radians per second. Make sure you have your units correct. Okay? Know what you're working with. 10 and 11, you're finding linear velocity. So it gives you R, it gives you omega. Okay, omega again is the angular velocity. So you're just multiplying your radius, which was 12 on number 10. Your angular velocity is 36. 12 times 36, boom, put in your calculator, 432, and that was inches per second. 11, same type problem. It told us our radius was 7. Our angular velocity is 5 pi. Multiply that, you get 110 meters per minute. Notice, pay attention to your units. Okay? And then the last one, 12, kind of an A and B part. Just like yesterday when it gave you something with the arc length and then you had to find the area, okay? Same type problem. For this one, we had to find the arc length first, okay, to figure out how far we went, all right? We get this for our arc length, and then we use that in this problem over here to figure out our angular, or our linear velocity. Okay, so if you look at 12, it says a geosynchronous equatorial. It says equatorial, which to me means it's going around the equator. I don't know if that's true, but that's what it seems like it means. Okay, so geosynchronous equatorial orbiting satellite. GEO. We'll just call it a GEO. Okay. Satellite orbits 22,300 miles above the equator of the Earth. It completes 1 full revolution each 24 hours. Assume Earth's radius is 3,960 miles. A says, how far will the GEO satellite travel in 1 day? So this is the first one. We have to figure out the radius. It's 22,300 miles. Was it miles or feet? Had to have been miles. Okay. It's that far above the Earth. The Earth's radius is 3,960 miles. Okay. So you have to add those up to get the radius. You got me? Times your 2 pi. This tells me how far we're going. Okay. All right. Was that 164,996.4 miles? It's a long way. Okay. Over here, I take my S and I plug it in because part B says what is the satellite's linear velocity in miles per hour. So I take how far it went in miles, divide it by how long did it take it to go around one time? 24 hours. And I get, can't grab it. Come on. It won't let me grab it. There it goes. 6,874.9 miles per hour. Per hour, whatever. you know, you get what I'm saying. All right. Y'all have 13 through 33 odd. I'm sorry there's not as many as you like usually. You know, I could give you more. You can do the evens if you want to for fun. Just kidding. For those of you at home, hope you enjoyed this video. See you next time and stay above the line.